First video is from chapter 2 is going to be on some basic definitions, so mostly the stuff in chapter 2-1. Okay, so first off, so kinematics. Kinematics is all about how objects move. So if you have, say, you know an object's initial position and you know its velocity and its acceleration and how the time, so say it undergoes the acceleration for 4 seconds, you can calculate things like how fast it ends up going and how far it traveled. Now, kinematics is all about the how, but dynamics is all about the why. So why do objects move? Why are they accelerating? Why are they speeding up? Why are they slowing down? Why are they changing direction? You put those two together and you have mechanics. So mechanics is both the how and the why, so kinematics together with dynamics, and we'll actually get to that in chapter 5, and we're going to be looking at Newtonian mechanics, which is the mechanics that originally Isaac Newton came up with. So, as is the tradition in physics, we're going to start simple. So we're going to be starting with translational motion. So and by translational motion, I mean just motion from some point A to some point B. So an object starts at one spot and moves or translates to another spot. So motion from point A to point B, and very explicitly, we are not going to be dealing with rotations, so things that are spinning, or vibrations, so things that move back and forth. Yet. So we will get to rotations a little bit later on in the semester. Now, and again, so in just a bit of terminology here, so especially when we start off in mechanics, we stick with something called particles, and by particles we mean a point-like object with no spatial extent. So in the no spatial extent part basically means that if it doesn't have a spatial extent, then it doesn't make any sense to talk about it rotating. So you really do just have to worry about the translational motion. Okay, so vectors. So vectors are quantities that have both a magnitude and a direction. So the direction matters. So, and this is just a quick intro. We're actually going to be talking more about how to deal with vectors when we get to chapter 3. But things like velocity and force and displacement and acceleration, all these things in physics are vectors. So the direction of these guys matters. So for example, if you think about velocity, well, velocity is how fast and in what direction you're traveling. So 40 miles per hour north is different than 40 miles per hour east, right? You're going to end up in different spots. So those are two different things. So it makes sense to have a direction associated with the velocity. Same thing with force. So a force is just a push or a pull, and pushing in one direction is different than pushing in a different direction, right? So something different is going to happen. So those things naturally have directions associated with them. Now, scalars, on the other hand, don't have a direction. So it's only a magnitude or only a number part. And these are things like temperature and time and speed and distance. So temperature, well, it doesn't make a whole lot of sense to talk about direction when it comes to temperature, right? I mean 72 degrees north or 72 degrees west by southwest, right? Those don't make a whole lot of sense. So it doesn't make sense to talk about direction when it comes to temperature or time for that matter. Now speed and distance, well, and again, this is where things get a little bit tricky. So the notation, and we have very specific language in physics, where velocity is how fast you're traveling with the direction, speed is how fast without the direction. So velocity is the vector, speed is the scalar. Okay, and notation-wise, so vectors are denoted by an arrow over the symbol. So if we're using an A to stand for some quantity, we draw an arrow over it to indicate that A is a vector. Now this is how your textbook does it. So there are other textbooks. It is common to see vectors written in boldface also. So I don't like this as much since it's a little harder to write boldface when I'm writing things on the board, but sometimes you will see that. So if we're only interested in the magnitude part of the vector, so the way you indicate that is with the absolute value bars. So if we have A, right, so A is a vector, so we've got the arrow over it, but then we put the little absolute value bars on either side. That means we only want the magnitude of the vector, so without the direction. Or you also see this as just the A without the arrow. That means, so if A is a vector, A without the arrow over it means the magnitude of vector A. And again, we'll be dealing a lot more with the vectors when we get to chapter 3. Okay, and a couple more things. So in chapter 2, we're going to start as simply as we possibly can. So it's going to be motion in one direction. So if we have one direction, that means we're moving along a line. And in general, we can be moving along a line, and it can be a horizontal line, so side to side or left and right, or it can be a vertical line, up and down. So the nice thing about one-dimensional motion is, well, in one-dimensional motion, we really only have two directions to worry about. So imagine we're moving on a horizontal line. So we can either go to the right or we can go to the left. So we can use signs, positive and negative, to indicate direction. Now, just one last thing. So we're going to be measuring the positions of objects and distances and speeds and things, and we have to measure these with respect to something. So, and the something we're measuring with respect to is called a frame of reference or a reference frame. Right, so imagine you're in the lab and you have little carts that you're moving along tracks. So a typical frame of reference is going to be the track or the top of the table. So that's what you're measuring with respect to.